Well, good evening, everyone. It's Friday night and 7 o'clock, and we're back for another round of intro to cross country topics. Tonight's topic is model-based weather forecasting. So the so here's the schedule. So April 5th, model-based weather forecasting. We have flight tracking and online soaring contest, and We Glide are the two remaining sessions that we have this year. Uh, just to be sure everyone knows, the presentations are made available on the SSA members website. So you can log in there. Notice it's members.ssa.org. And once you're there, you go to my homepage, go to news and resources and webinars, and you'll find the list of webinars there. If you click on the webinar title, you'll get the recording. We are recording this evening. And if you click on slides, you can download the slide presentation. So you can have that while you're listening. Um, so again, we want to thank the SSA for making the webinar software available and for Frank Whiteley for doing the hosting for us. That keeps us up and running. Our courses, these seminars are eligible for Wings proficiency or Wings credit. And we have 3 members of our club that are on the FAA safety team for Wings. If you registered with your Wings user ID, the credit will be applied over the next few days. The FAA guidelines is the online seminars count for Wings credit, but it's only the live seminar. Viewing the recording does not count for Wings credit. And then we have some of our club instructors that are hiding in the background. So if you do questions, they will try to answer them. We will have time for Q&A at the end of the presentation. So, but we appreciate what they're doing for us. Okay. On the left of this slide is a QT chart generated from a radiosonde, or it might also be called a raw wind sonde. I'll explain that in a little bit. And so from that, we get temperature, dew point, wind direction, velocity, all plotted for altitude. And on the right, what we have is for the GOES satellites. These are the National Weather Service satellites, the geostationary operational environmental satellites. And they run 2 of them at geostationary altitude, one at 75 degrees west longitude and one at 137 degrees west longitude. And you can see their fields of view. Acknowledgements. Jack Clendenning, Dr. Jack as we all came to call him, and came up with the in mining the data. You know, he's a weather scientist. In mining the data for trying to come up with soaring forecasts, he came up with the initial tools going back to the early 2000s. And so an awful lot of what you see, you know, what we have today, 25, 24, 25 years later, is somewhat based on his work. And he did some pioneering work for us. I have Dave Leonard listed because he maintains the Colorado RASP, the regional soaring forecast. And so that's the Front Range of Colorado, and I'll show that to you later. And then the other one is Matthew Scudder, who has created the SkySight forecast tool, which has moved us into some rather interesting directions. So our purpose is to describe the forecast tools, and we'll go through some history so that you get an understanding of what weather or model-based weather forecasting is. And then I'll have a RASP slash SkySight demo later on. Now, what you have to remember, you know, it seems like I start every one of these things off with, well, you got to remember this. Okay, the National Weather Service mission is to provide weather, water, climate, forecast, warning, and impact-based decision support services for the protection of life, property, and enhancement of the national economy. Now, National Weather Service has plenty of aviation products. However, they work in a very different problem space than what we need as soaring enthusiasts. And fortunately, we've had weather scientists and people that work for National Weather that are also soaring pilots, and they've adapted the existing products and developed and evolved tools uh, and processing techniques to give us the soaring forecast mechanisms that we enjoy today. So these things are, while they're based on national weather uh, products, our soaring forecast tools are not national weather products. Some of the things that you can get, I have three of them that I like to look at that are just general. The first one is the advisory watches and warnings. So this one was from yesterday, and excuse me. Uh, so this is a high wind warning area, and we're under high wind watch right now. The cream out here, this is called a fire weather advisory area. The pink areas right here are red flag or a red flag warning or high fire warning. There's actually a little section of winter storm warning in the south central portion of Colorado. I also thought it was interesting. This blue area right here is a frost watch, and then the uh, brighter blue area is a frost warning. And when I looked at them this morning, this had expanded down into Arkansas, and this went up into Iowa and across. But this gives you a quick, if we were sitting under a high weather warning or high wind warning, for instance, in our area, it's probably not going to be a good soaring day, just to keep things like that in mind. So I find that to be useful as a broad brush. Then we have the typical aviation surface prog. And again, this was yesterday. Um, so you can see a low over here on the East Coast. That should still show up a little bit in the satellite images we look at later. You can see that we had lows with a trough in between them and a couple of highs sitting out here and a real deep trough right here. So that actually blocks the moisture coming up from the Gulf area. And then there's also the weather aviation observations. And the nice one about this is this gives the snapshot of the airports that are reporting or the sites that are reporting. You can zoom in down to the low level, you know, instead of just seeing Cheyenne and Denver, Colorado Springs and Pueblo, you can zoom in and see a lot of the others from here. Notice this has some of the status stuff that we were just talking about, and it also has some radar. So that's what the green and the bluish is different radar returns. So, and then off the West Coast, this is small craft warnings. So this one gives you a nice, again, a quick overview summary to work with. So when we start talking about weather modeling, um, the U.S. government in some form or other has been recording weather observations going back into the 1800s. But the forecasting was based on the experience of the individual forecasters, and there weren't any formal tools. It might be a pretty good, just a guess or that kind of thing. A milestone was in March of 1948. On March 20th, a major tornado hit Tinker Air Force Base in Oklahoma. And at that time, Tinker was a huge uh, maintenance depot and storage for surplus aircraft. The tornado came through. It had, their warning was when it crossed the base boundary. It damaged or destroyed 54 aircraft and damaged numerous buildings. Fortunately, there were only 8 injuries and none of them were serious, and there were no deaths. The commanding general for Tinker uh, grabbed his weather team and said, you know, you guys can tell me it's going to rain. Why can't you tell me we're going to have a tornado? And so the two folks that are mentioned in this plaque, Major Ernest Fallbrush and Captain Robert Miller, were tasked to come up with a method to forecast tornadoes. And the stories that you read indicate that basically they didn't sleep for a week. They were going through all kinds of empirical data, trying to come up with patterns that they could use that would allow them to identify the likelihood of a tornado. This is going to sound really weird, like somebody was doing something strange, but just 5 days after that first tornado or that tornado hit the base, these two gentlemen issued their first tornado warning based on their model that they put together over this 5 day period. The warning allowed the base to secure its operational aircraft in hangars and such and to move their personnel to safe locations. The second storm came through the base and tracked within 100 yards of the earlier storm. It damaged or destroyed an additional 85 aircraft and additional buildings on the base. This time there were no reported injuries and no deaths. Okay, so the important thing here isn't uh, that they prevented damage or they prevented injury with their forecast. It was they forecasted early enough that the disaster preparedness response system for the base was able to respond, and the tornado showed up pretty much basically when and where they said it would, and it traveled the range that they said that it would. So what they were trying to do is create a model that they thought would identify conditions indicating the possibility of a tornado, and they were extrapolating direct atmospheric observations. So things from the radio sondes, ground observations, that kind of thing. Today's forecasters are using models that derive both from direct measurement and remote sensing observations. The modern model-based forecasting uses both types of observations to initialize the models. So then that provides insight for areas that do not have direct measurements. And I'll show you some examples of that here in a little bit. Further, the examination of the large data sets, once they were able to get out, these two guys ended up being the genesis of the Air Force's Severe Weather Forecast Center. By looking at the very large data sets, they were also able to identify larger scale phenomenon that, you know, being on an individual base or in a community with just that location's data didn't allow them to see. Okay, some definitions as we work with this, because weather people talk in terms that we don't necessarily know or understand. And so when we talk about the boundary layer, okay, that's the active layer of the atmosphere. It's generally 1 to 4 kilometers thick. So from about 3,300 feet above the ground, you know, it goes up to about 3,300 feet and then up to about 13,000 feet, depending on the conditions. This is the planetary boundary layer. This is the layer where the effects of friction, so the Earth imparting friction on the air mass above it, winds and stuff like that. This is where the friction effects are significant. The other one is, just because they say it's the top of the boundary layer, that does not mean that convective activity stops at the top of the boundary layer. You know, at least in our part of the country, we see thunderstorms punch to 45 and 50,000 feet. And I imagine down along the Gulf Coast, they go even higher. So for the Earth, this planetary boundary layer, or what I'm calling boundary layer, there's two components to it, and we'll talk about the second one here in just a moment, is, like we say, the lower 1 to maybe as much as 4 kilometers of the atmosphere. It's within this layer that the temperatures are most strongly affected by the daytime heating from the sun and the nighttime cooling for radiation cooling. The winds are affected by friction with the Earth's surface. the effects of friction die out gradually with increasing height, so the top of this layer really can't be defined exactly. There's no particular boundary that says it's the top of the planetary boundary layer. And it's not like the difference between uh, the tropopause and the stratosphere, or that kind of thing. We don't have that kind of defined, distinct boundary. Now, within the overall planetary boundary layer, there's a surface boundary layer. Uh, Now, sometimes you'll hear it called just the surface layer. This is only a portion of the planetary boundary layer, and it represents the layer within which the friction effects are more or less constant, as opposed to decreasing with increasing height. The surface boundary layer is roughly 10 meters thick, so from the surface up to approximately 10 meters. But again, the exact depth is indeterminate. The effects of the heating and the heating components during the day and the radiational cooling at night are strongest in this layer. And you'll find that AWAS towers, we'll talk about those in a little bit, but the remote reporting towers that we see at our airfields make their surface wind measurement at 10 meters above the ground. As we look at the other terms, the synoptic scale, uh, synoptic scale refers to large scale or cyclonic scale. So this is the size of big weather patterns. This can range up to 600 miles or 1,000 kilometers across. The things in this scale could go up to, 1,500 miles across. Okay. Mesoscale is the next one down from synoptic, and it refers to weather systems that are smaller than synoptic scale systems, but they're larger than storm scale systems. Okay, so this isn't a single thunderstorm. This might be a squall line moving across the plains. Okay, this might be a major snowstorm or winter storm event that covers a couple of hundred miles, but not as big as maybe a major northeaster running down the East Coast. Okay. Generally, what you're talking about here is you're talking about effects that are somewhere from 50 to several hundred miles. The microscale, this is referring to storm scale. Now, a thunderstorm, how much of an area does a thunderstorm influence? Well, directly from the thunderstorm, it's a few miles, maybe 10, but then it has a track. And of course, if we kick a tornado out of it, then we were following that. But from the big picture for national weather, that kind of a storm all the way up to a hurricane could be considered microscale storm. Now, synoptic scale models show trends. Like when I put the prog chart up and I made a comment about the front and the location of the highs and the lows and made a remark about blocking moisture coming up from the Gulf. So synoptic scale shows trends. Mesoscale models are pretty good out to about 3 to 5 days. The modeling tools at National Weather are improving, but still, then you have the microscale models, and generally they start to break down at about 3 days. So when you're looking at any of these modeling tools, um, the next day, today, the next day, and maybe the day after is probably not bad, but some of the tools will go out for 6 or 7 days. And basically anything beyond 3 or 4 days is, yeah, just watch it and see how it changes. Don't bet on it, okay? In soaring, we're basically working somewhere between the microscale and the mesoscale when we're interested in the weather phenomenon, what it's going to do for us. Two other definitions, the RASP table GM. This is a browser-based visualization tool using Google Maps. And then the Univiewer, which is a cross-platform visualization tool that is used for earlier versions of some of Dr. Jack's materials. Today you look at it and it's extremely painful to use, but it's still out there. All right, when we have the weather models, we've got to initialize the weather models from something. So we have direct measurements. So these come from surface measurements, uh, the AWAS tower, the weatherman going out and reading the stuff in the little white box on the side of the airport. Um, and we also get atmospheric, like the radiosondes. So this is actually measuring the phenomenon, you know, reading the thermometer, reading the anemometer, reading the pressure or dew point, those kinds of things. Okay. And then we have remote observations, and a lot of this is Earth observing satellite instruments. And right now, National Weather is working. I showed you the geostationary birds location for GOES, and then there's some polar orbiters that fill in other data. But basically, we're talking about our Earth observing satellite systems. The numeric models, they predict behavior. Different models target different behavior. The other thing that's interesting is National Weather has models that cascade. So I can run a model and then use it to initialize another model. Okay, so these models can be used as building blocks. They can be linked together with the output of one feeding the input of another. Okay. The key with all the weather models is the results have to be interpreted. So you've got to look at it, or you've got to have a weather briefer that looks at it and then says, okay, this is probably what this means. Now, again, coming back, I think going all the way back to the first session in this year's series, models are an abstraction of reality. Okay. They've simplified reality so that they can see if they can identify things and make decisions based on it. But it is not reality. It is a view. Okay. Um, so these models can be manual, they can be automated, they can be a mix. Um, they may need to be tailored to address the specifics of its usage, perhaps of its location. Okay. And as we go through the demo of the two modeling tools that I've chosen for this evening, we'll talk about interpreting what we're seeing on the screen. So direct measurement, this is where we're actively and directly measuring something. The first one is the NEXRAD radar sites. These are Doppler radars. This was a huge leap forward when these things came online. These little radar systems punch out uh, to a couple of 100 miles. You can see the coverage there. The yellow is the bottom of the coverage at 3,000 AGL. The goldenrod, or the darker yellow or orangish kind of, the bottom's at 6,000 feet, and the blue is at 10,000 feet. So you can also see on that by looking at where the holes are. Well, we don't have a lot of people there, and we're not trying to provide the level of protection that we are, say, up and down the East Coast or along California, or even like for us in Colorado. We have five overlapping sites that feed in Colorado. So Grand Junction, Cheyenne, Goodland, Denver is at Colorado Space and Airport, and then Pueblo down here. So we get good coverage here in Colorado. There's 160 of these sites across the U.S., including Alaska and Hawaii. If there's no precipitation, then in clear mode, the images are updated once every 10 minutes. If there is precipitation that they're tracking and the possibility that they're tracking storms, then the images are updated every 5 to 6 minutes. The real thing that these radars do is they give the forecasters, the uh, the weather experts, a method by which they can characterize severe storms. The next one, we have the direct measurement Raywin Son sites. I stumble over that word every time I say it. Okay, so these guys are used for input to computer-based prediction models, local severe storm, aviation, fire, weather, marine forecasts. The data is used for weather and climate research. They're also starting to pick up information out of this for air pollution models, primarily using the aerosol movement in the atmosphere. And these provide a ground-based observation that it can be used for truth to compare against the data that's coming down from the satellites. One of the things you always have to do is you have to cross-check your data and make sure that it correlates correctly, that you don't have something that's wildly out there. The radiosonde's onboard instrument package measures pressure, temperature, and relative humidity. If it's tracked when it's flying, then the ground tracking system, you'll get wind speed and direction. So the reason I stumble over Raywin sonde as opposed to radiosonde is they replace radio at the front with this RAWIN to mean radar wind. Okay. So most of the radiosondes that are flying have radar reflectors in them, and so the ground radars track them. This is a direct measurement system. You take a look on the map, you can see that in Colorado, they launch out of Grand Junction and they launch out of DIA. And so there really aren't as many of these sites. There used to be, a whole bunch, a lot of flight service stations, not all of them, but a lot of flight service stations would send up balloons. So the various colors depends on who owns the particular site. Some are part of the Global Climate Observation System, and others are part of the National Weather Upper Air Program. The other direct site or direct measurement that we have are ground measurements based on observation stations. You probably heard the acronym of AWOS, so Automated Weather Observation System. And then there's ASOS, Automated Surface Observation Systems. Basically, they're very, very similar devices. AWOSs are generally associated with aviation, and an ASOS can be anywhere. For instance, there's one in Central Park in New York City. There are over 900 stations nationwide. Okay, here's the Colorado distribution. The ones with the blue markers, those are the Mountain AWOS program that the Colorado Department of Transportation, through their aviation branch, has placed out. For instance, you can see this one's at Wilkerson Pass, and these others on the mountains. And so this is Colorado Department of Transportation giving us observations in places that we didn't have observations before. The yellow markers are general aviation airports that have an AWOS. The red markers are commercial airports, so Pueblo, Colorado Springs, Denver International. All right. And then there is one lowly little purple one right here at Meadow Lake, and that's basically, it's a private airport that has an AWOS on the airport. So the inputs from all of these direct measures make their way into the models to help initialize the models. Now, the next method is the remote sensing. So this is where we observe something from a distance, and how we observe it allows us to determine some of its characteristics. And so basically you can say how we look at it tells us something important about it. The picture on the screen right now, that is the GOES-R or GOES-16. When they're under development and before they launch, they're referred to by a letter. Once they've been launched and they're on orbit and have completed their checkout, then they're given a flight number. So this is GOES-16, which is our GOES East satellite. This is in a clean room at Lockheed Martin in Littleton, Colorado. You can see the solar array, and you can see the gentleman standing next to it, the other gentleman here, and this is the main bus on the satellite. So you can get an idea of how large this thing is. This is a new satellite family. The first one launched, 16 launched in 2016, 17 launched in 2018, 18 launched in 2022, and 19 will go up. It's expected to go up this year. This family of 4 satellites, what is expected to last until 2036. So if Ghost 16 lasts all that time, it will be 20 years old. The effort to describe the capabilities of the next generation satellite is already underway. So the and a couple of things. Let's see if I can do this. Give me a moment because I want to get you no. Well, all right. I apologize. I was going to have a video of the launch of the Goes T number 18, and I can't get to it right now. And the other one is I was going to show you the lightning mapper on Goes 16, where you could see a storm moving through the Midwest overnight, and you can see the lightning. The global geostationary lightning mapper, the intent behind that instrument package is to gain an understanding of the severity of storms, and hopefully can use it for can be used for future uh, prediction, severe weather prediction. Okay, at this point, we've got we're going to take a look at some of the views. So when we are looking at these, we have okay, that didn't go where I wanted it. National Weather maintains these instruments and their data for us. And so the imagery is full disk imagery. The GOES satellites, the current generation satellites, they call them the GOES-R series, can image this full disk of the Earth in as little as 5 minutes. The imagery is at 1 kilometer per pixel. And so gives a real nice view, and you can see it in animation as well as, so you can see the clouds moving, you can see the Terminator moving across. The city lights that you see do not come from the GOES satellites. They come from another NOAA, National Oceanographic and Atmospheric Administration satellite. And then they're placed on these images, just like state and county outlines, to make it easier to see where the phenomenon are. So this is a full disk image. Notice that it's all the way down into South America, and you can see some huge storms building down here. You can see the pipeline over here on the right-hand side. Um, and that pipeline over there, that's the later in the summer, that becomes the pipeline for the hurricanes. They start in thunderstorms on the coast of Africa, move out over the ocean, cross over, come over towards the side of South America, and then move up and pick up energy from the warm waters in the equatorial regions. Okay, that's full disk. We'll go back to synoptic. Synoptic, and I'll just bring up the animation. This is the full United States, so 3,000 kilometers north-south and 5,000 kilometers east-west. The full disk right now is updated every 10 minutes under the current strategy. The CONUS for this image is updated every 5 minutes. And so we can see the clouds moving in, streaming in. We can see that trough that I pointed out from yesterday. We can see the dry area clearing in with the downslope winds and that kind of thing right here. And we
Dave,
can
we're not seeing any changes in the slide. We're still seeing the slide with views, full disk, synoptic scale,
ah,
etc. But we're not
thank
seeing
thank
the
you.
USS.
I didn't realize I had done that. Ah, there we go.
That's better. Thank you.
No, I appreciate the comment. I didn't look over my right shoulder at my other display. So I'll go back and give you the full disk just so everybody gets to see it and it wasn't just me talking about it. So there's what the full disk looks like. The geostationary birds sit over top of the equator, and they sit out at roughly 24,000 miles, 40,000 kilometers above the Earth. And like I said, this image is refreshed once every 10 minutes, and the pixel image resolution is 1 kilometer square for the imagery. A mesoscale. So we're going to come in. I'm going to go over here on the east bird and pick up the Northern Rockies. So you can see Salt Lake right here on the left. Come over, you can see this is the image of the Front Range lights. So Denver and north, a gap, then Colorado Springs, another gap, and then Pueblo. You go north, the lights are Longmont, Greeley, uh, and on up to Cheyenne. Notice that we can zoom in and get a nice tight image. So the
Dave, your screen is zoomed in a little bit. Do you want it that way?
yeah,
Okay.
yeah, because you can see the county boundaries that are on there. So we can get this down to fairly small for something to work with if you wanted to look at the imagery for your area. Now I'm going to put the animation up on this so that you can see the animated loop. So you could, conceptually, you could download these into your cockpit, but I'm not sure, you'd have to have a pretty good data connection and stuff like that. I'm not sure how much that would be useful to you as opposed to just looking out in front of you. Now there is one other that I want to show you from meso or micro, I mean. And this is a resource that we have on our club webpage. This is the GOES 16 image. It's going to take it a moment to come in. And this is maintained, this imagery is coming from the University of Wisconsin. So, and it will take it a moment to, each time you see a flash, that's a different image. These images are uh, 10 minutes apart. And if we wanted to, we could come in here and zoom in. So if you really wanted to get close, this little square or this little cutout right here in the bottom center, that's it's a funny with El Paso County. It's a cutout to make sure that Pikes Peak was in El Paso County. And it's just a nice little piece of data for you. All righty. So, and we're back. Okay. So those are resources that are available to you if you want to chase them, and then after you look at the models, pull up the cloud patterns and stuff like that to see how it looks to you. So, all right. Now, the weather models. There is the NAM, it's the North American Mesoscale Forecast System. It's run 4 times a day. These are all UTC, so midnight, 6, 12, and 1800. It goes out for up to 84 hours, and it uses a 12-kilometer horizontal resolution. And I'll show you, next slide, I'll show you how this works. There's the RAP, it's the rapid refresh. It updates once per hour. Its forecast only goes out 18 hours. And depending on the setup for the run, it may be 13 or 20-kilometer horizontal resolution. And then the WRF, this is the weather research model, feeds an advanced research weather model. And so this is another one that we end up using, and that comes out with a 2 to 6 kilometer resolution, depending on the settings for the run. Another model that you have probably heard of over the last 4 or 5 years, it was experimental about 5 or 6 years ago, and it's now come pretty mainline. So the RAP was a 13-kilometer resolution model, or about 8 miles. There's another one called the High Resolution Rapid Refresh. You've probably heard it as HRRR. It generates down to a 3-kilometer resolution, so 2 miles. And so what you use that for is they run that over smaller areas. The so, and to give at least our club members a point of to anchor these dimensions on. The runway at our airport is between 3,500 and 3,800 feet long, and so that's about 1.2 kilometers. So when we say this is down to 2 or 3 kilometers, you can get an idea that if you had a square on the Earth that was, 3 one-way links east-west and 3 one-way links north-south, that is the resolution of the forecast. Now, what does that mean? Well, what it means is they've got a grid pattern of the Earth. And so the one that's showing right here is for Southern California down into Baja and the northwestern part of Mexico. And you probably can't see it on here, but I'll outline, but there's a square right there. Okay, and then that square is subdivided. So you can see if this was that one square, so it's been subdivided into 4 by 3, and then it's got an altitude to it. Okay, so we've got, for all intents and purposes, what looks like a big Rubik's Cube. And each one of the cells in the Rubik's Cube has a forecast, and then that forecast is normalized between all of the other squares, cells in that Rubik's Cube that touch this particular one. Okay. Smaller cells means that we get a better idea, but with smaller cells, the execution time of the models get longer and longer because we're processing more data. But what this does is this allows us to lay this on top of the terrain. So if it's mountainous or if it's plains, if it's water, that kind of thing. And so we can adjust, we may adjust the resolution. If we're out over the ocean, we may use a coarser resolution than what we would use over land. And then it also gives us a method of talking about the phenomenon. You know, could it be contained in one of those squares? Does it need to be larger? That kind of thing. Now, one of the things that the models allow us to do is it allows us to create virtual sites. You know, so remember I said that the radiosonde sites in Colorado were Denver and Grand Junction. Well, this is a tool that's run in the RASP, and each one of these little stars is a soaring site in Colorado. So the one I've got my little pointer on, that's Black Forest. Here's Meadow Lake. Here's the Air Force Academy, Boulder, Colorado Soaring Association up at Owl Canyon up here at the top of the map, Eagle Soaring over here at, I think it's by Steamboat, Salida, Colorado, Canyon City or Fremont County Airport, and then Silver West Airport, and I think that's La Veta Airport right here. Now, what we can do is we can take the model data and create a virtual skew-T chart, okay? So that we could then get an understanding of the atmosphere as produced by the model at that location. Okay, so basically we could create a virtual skew-T chart for any location in our soaring area if we wanted to go down and do that much work and see that level of detail. Some of the later models like SkySight will allow you to do point forecasts, but it doesn't limit it to just presenting the data like a skew-T, and I'll show you how that works when we do the demo. So for something that's virtual, basically you can see it, but it doesn't physically exist. There is no launch site. There is no launch site on this right here at Salida, Colorado. There is no balloon launch site there. So what we've done is, using this tool, they've created a virtual site so we can click on that and get a skew-T chart for Salida, Colorado Airport. When we look at the models, a couple of the free models, now this really isn't exhaustive, but we get BlipMap, which is the early Dr. Jack model, and then that evolved later and created the RASP, which has gone through several iterations and is up. It's a fairly usable model, but these are free. The BlipMap was run on a central computer. The RASP, the R stands for regional, and so there are volunteers around the country that are doing the model runs for a local or regional area, local to some specific soaring sites. So these are done by volunteers who are volunteering both their time, their expertise, and their computing horsepower. There are two subscription, or at least two subscription services. One is Top Medio, which is the guys come over from Europe to the convention. And then there's SkySight, and that's Matt Scudder's software. You can see the prices. I've talked to the folks from both groups. I've talked to Matt directly. I've talked to the people that represent Top Media. My personal opinion is the Top Media folks, it was a lot of hand waving and yeah, we have lots of experience and we know what we're doing. And when I talked to Matt about SkySight and indicated there were some things that, I was seeing, he was really willing to discuss their approach and provide adjustments if their model wasn't working correctly in our area. So you can probably tell from that description where I spent my money. One of the things that our club has done is we have SkySight available to the club members on the club computer in the clubhouse, so they can come in and use that in their pre-flight. And then RASP is also available because that's a web-based interface. The early soaring models, BlipMap goes back to about 2000. This was a real breakthrough at that time. It was first done in California and then later out into regions across the US. The RASP came in later. It's more complex. It's now running like a forecast model. It doesn't run just one time during the day. It runs multiple times. And so it was a great improvement. And then when we got to bring it over to putting it on Google Maps, that improved it even further because now we could have landmarks in the background and without just dropping pins everywhere to be sure that we could track where things were. The soaring parameters, okay? Now, these are very similar in all the models, but they're not exactly the same. So you will have these parameters. So some parameters are derived from the input source model. Some are presented directly from the source model. So for instance, CAPE down here, the convected available potential energy. Okay. The soaring models don't calculate that. That's coming directly in from the Weather Service. Others are composites. So for instance, the first one up here on the list under the thermal parameters, it's thermal updraft velocity and buoyancy shear ratio. So the thermal updraft velocity and the buoyancy shear are merged and put on a single presentation. And again, I'll show you this when we do the demo. We get thermal updraft velocity. We get the height, so we can get the thermaling height. It's interesting. The thermaling height is funny because there's one school of thought that says it's when the thermal drops to 175 feet a minute. And there's another school of thought that says, well, it's when the thermal drops to 225 feet a minute. And you kind of go, oh, okay. I hope nobody, committed mayhem over the difference. Wind parameters, we get wind speed and direction, both as a combined or as individuals. Another one is we look for boundary layer convergence. So in the RASP model, it's called boundary layer max up, max down motion. In SkySight, it's just called convergence. But this gives us areas where we may be seeing actual convergence because of wind differences, or we may be seeing something as a result of the terrain or something else. Cloud parameters, one of the things that they did was take the cumulus cloud base, and they said with as long as it was potential to have clouds. Same with overdevelopment. They put two values in there which said the overcast cloud base and the potential for overdevelopment. So these are the kinds of things that get fed or that come out of the models that we look at. The other thing, quite by I guess I could almost say it was quite by accident, at least the way it read when I read the article on it, it sounded like it was quite by accident, is they started detecting wave. So if you look over here, you can see wave bands in the red box. And if you look at the green box, you can see this reddish yellow line. And what that is it's predicted wave activity based on the wind speeds and the stability of the atmosphere with the likelihood of vertical motion. And I thought that was real interesting. So this starts to get into our wintertime flying or maybe our late spring and late fall. The other thing that this started turning up is when they started looking at the motion of the wind and its effect as it moved into other air masses. So you can see this line of clouds right here on the radar image. And this one is not rotated the same angle, but you can see this line and a line going up over here to the left and splitting. And what they're doing in this one is they are uh, seeing the result of the impact of air masses that are moving in different directions. And one of the air masses will end up going up and the other one will end up going down, but it will create a convergence line. And getting this. Now, the problem with this is this phenomenon is not very wide. So you end up having to run, a fairly fine scale resolution in order to be able to see these kind of things. The Colorado RASP, when we get to that, we are, this runs from a line through Scotts Bluff and Rawlins, Wyoming at the north, south to just north of Santa Fe. On the east, it is in between Lahana and Lamar out on the eastern plains. And on the west, it's a north-south line through Grand Junction. And this model is run, the fine scale model for the current day is run at 2.4 kilometers grid. So this is a fairly fine scale model. And the virtual RAOB sites are out there mainly because when you start adjusting the saturation of the colors, those dots stay, but the background terrain disappears. And so it gives you a nice anchor point to understand the phenomenon. When we are looking at forecast parameters, no single parameter that is output from the soaring model system predicts everything. The parameter forecasts can be used to cross-check each other. So for instance, you could use the cloud cover along with sunlight hitting the earth to cross-check whether the model is saying, oh, there's clouds and that's going to cut down the amount of sunlight that reaches the ground. If they are at two different extremes, then that tells you maybe there's something in today's run that didn't add up quite right. And so, be quite, question whether or not it's going to overdevelop or question whether or not you're going to have that much sun on the ground. The parameter forecast can be combined. That's what I call the composite ones. And there's far more parameters in these models than what we're going to discuss. So, your homework assignment is to go pull up the model and, get an understanding of the ones I'm going to point out to you. But at the same time, be sure that you go get an understanding of the ones that I didn't talk about. You may find one that's a nice corner case and it answers some questions for you. When we look at RASP versus SkySight, RASP is a weather forecast only. It is today plus 2 days. It has an older user interface. It's not a bad user interface. It's just older than something that was put together in the last 5 years or the last 10 years, okay? SkySight does weather forecasts. It attempts to do today plus 6 days. Be kind of careful once you're out past 3 or 4. Take it as advisory. The idea might be if you looked on Monday and you were hoping for Saturday or Sunday, you might see a pattern that then you watch to see if that pattern develops as you get closer. Don't bet the farm on a 6-day out forecast. It does have an improved user interface, and we'll be pointing that out. And it has flight planning capability. You can do a route forecast and then run through the time period of the flight and watch the weather parameters change. And then it also has a point forecast, so you could look at a specific location, and I'll show an example of that when we get there. When we're talking about the RASP, this is a web-based system. You open it in a browser tab, and let's see, let's switch this around again. All right. Okay, this is what the RASP display looks like. This is zoomed in. You can zoom in by either using your mouse wheel, or down here in the bottom right-hand corner, there's a plus and minus that you can use to zoom it in. If you want to adjust it position in your screen, grab it left click in the middle of the map, grab it and drag it, and it will move around for you. Okay, I'm going to zoom in just a little bit further. That's about right. In the top right, this box in the top right over here has the forecast days, so you can go yesterday, today at 2.4 kilometers, today at 4 kilometers, and then tomorrow and the day after, both of those will be at 4 kilometers. These are all time sequenced, so you can select the time. I've got this one set at 1400 local. And then this is a list of the parameters. The parameters that we probably most look at are highlighted in blue. And so I'll click on this one and you'll see the display change. Okay, so we'll come back to that in a minute. If you have a parameter highlighted, there's a question mark right here. You can click on the question mark and it will give you a description of that parameter. And it's pretty good at being written in layman terms. Down in the bottom right, you can select either having a Google map as your background, or you can select having a satellite image as your background, but I don't see anything worthwhile. I leave it on the map. In the top right corner, okay, you notice that when my cursor is moving around, I move between colors, but there's no numbers on the screen. The information is contained in this color bar over here on the right-hand side. So we're looking at thermal updraft velocity. So down at the bottom is 50 to 100. So these go in 150 or 50-foot increments, and all the way up to 1,000 feet per minute. Well, there's no 1,000 feet per minute on the map, but it gets kind of hard to tell where the boundaries are. So this slider up here allows you to adjust the color saturation. Now you see why the red dot for the particular airport is useful, because that's Kelly. That's our Black Force Soaring Society. Here's the Air Force Academy. There's Salida, and here's Fremont County Airport. This is Meadow Lake Airport. But now, with it fully saturated, you can come over here to the color bar, and let's go to the solid yellow. And so that says that there's lift. The forecast that was run for today for 1400 said the solid yellow was 550 to 600 feet a minute. So we somewhere in here, 5.5 to 6 knots where it's bright yellow. Where it starts to go to goldenrod, it's 600 to 650. Where it goes a little darker, it's 650 to 700. But notice as we cross over into the mountains, the predicted thermal velocities drop off dramatically.
Dave,
they're
can
not.
you slide a little bit over to the right so they can see the color bars? It's zoomed in pretty far for the, there we go.
No, the color bars are over on the right-hand side of the screen. I can't move those.
Okay, I can't see them on my screen. Sorry. Okay.
Oh. Um, so the slider up here allows you to look at a parameter, and then if you want more detail about it, slide it over, and then you're, like I say, you find this. I use the yellow, the straight yellow color. I go over here, find it in the color bar that's on the right-hand side, and then I can move up and down. So for instance, this is thermal velocity. Let me put in thermal height. Okay, so in this case at 2 o'clock, we've got thermals, this purple right here in the middle, that is over 17,000. Okay. And you can see bands. Okay. So the height for these bands are probably not the result of pure thermal activity. These bands may be the result of convergence or wave, but they're not, the look of them is not just pure thermal. So like everything else, when you're interpreting this, using it for a while gives you some insight. Notice that we have an area up here that's saying this isn't going anywhere. I have no idea what's happening there, but that tells you that there's nothing going on right there. And again, this is fully saturated. If I bring it down to about 50%, then you can get the idea of the terrain behind it. So here's the Front Range, the Rampart Mountains. Here's Pikes Peak, the massif for Pikes Peak. Down here, I'm going to shift the map up a little bit. This is the Sangre de Cristo mountain range. Notice that it's real strong purple right here in the middle. This is the San Luis Valley. It's a huge flat area with the wind coming in, hitting that, going up. Notice that it's cool right here, not showing much. And then we pick it up again. This is the Wet Mountain Range on the east side of the Wet Mountain Valley, or the West Cliff Mountain Valley. So that's how you interpret, that's how you work with these guys. So just a second, I'm playing with something in the background here, and it isn't working. All right. So when we go over to SkySight, looking for the same kinds of things, the color systems will be pretty much the same. Warm, for whatever you're looking at, warm colors usually mean good. Cool colors usually mean that's not where you want to be. So in this case, we started with thermal strength, and SkySight does thermal strength plus buoyancy shear ratio. The buoyancy shear ratio is the ratio of the crosswinds versus the vertical in the thermal column. So the idea is you have winds that will shear off the thermal. If it's extremely low, like you've got strong crosswinds against the thermal, then soaring flight might not be possible, or it may take a very good pilot in a very, it might be the day that only a 126 stays up. As the ratio gets higher, you get up into the range of 10 or something, then the crosswinds that are shearing the thermals have very little impact on the thermal. So the stippling, so notice that we've got light dots in this area, but notice we've got heavier dots up here. So what's that saying is where the heavier dots are, there's more shear in that area than there is in the other areas. Now, you'll also notice, I'm going to put it on the kind of the pink. If you look at the pointer, ahead of my pointer, it says 6.5 knots. So what's happening with this is the user interface isn't making you go over to the side color bar. It's actually putting the middle value of that color bar at the tip of the at the tip of the pointer. So it's 6.5 in this kind of pink color. And if I go to the yellow, it's 5.5. And if I go over here to the green, it's 4.5 knots. Okay. So that's one improvement. I don't have to play with the saturation on this to get the values. The other one we looked at was the height of thermals. And so this ought to be interesting because we're going to go down here and notice that we've got something similar with the heights occurring in this model as we did in RASP. Okay, there's nothing that says these two models are running the exact same algorithms, you know. So notice that you see that there's nothing marked over top of the peaks, and then there's some downside on the downwind side, and then we got the building again. Now, one of the things that SkySight will allow you to do is to use SkySight model, and it will also allow you to use the HRRR. And I find using both tools and all three models kind of helps because, like, notice the height of these thermals are still showing basically where we saw them on the RASP, maybe not quite as powerful, but it's on the HRRR, it's showing this, they're showing in this basic same location. And if I go back to SkySight, they'll show here. Now, there is one little interesting tidbit about the National Weather Service's models. One of the parameters in the model is soil moisture content. And as you can imagine, soil moisture content would have an impact on developing thermals. Unfortunately, for soaring purposes, National Weather uses soil moisture content as a correction factor to get the rest of the model to come in to reality. Matt Scudder has started working with a different model for his source input that comes out of Europe that does not manipulate the soil moisture in order to affect the overall model's performance. And so I'm not sure when that comes online, but it will be interesting to see how that changes the way the models look. But, you know, this, like I said, these are cascaded tools. So we start, you know, National Weather starts, they run a model, then they take the output of that model, run another model. We're taking the output of that model and running our models. So it will be interesting to see how this moves forward. Okay. All right. So height of thermals, uh, the strength, we can come back over here and look at the thermal. And I'll bring this in with a little more saturation. So not too bad out here on the plains, not real good as we go back into the mountains. SkySight, if I zoom it out, SkySight says near plains are not too bad, but SkySight is somewhat more optimistic as you go back into the mountains. And that's not a criticism of the model. That's just a difference in the way the model runs are handled, you know, the data that comes out of them. So no one parameter is correct under all circumstances. If I switch this over to HRRR, it's even more optimistic on thermal strength back in the mountains. So this brings us back around to a concept called model validation. Which one's right? Well, right now, I can't tell you which one's right. How do you find out which one's right? You go fly. And you will, over a period of time, develop a confidence in one or other of the models, or you will look at the kind of weather pattern that the model is operating within, and that will give you the clue about, you know, is this real or is this more real? Okay, that's where your experience of working with the models and then flying the area especially in the spring and fall when I'm not trying to do long distances or not trying to accomplish a specific goal. I'll do the forecasts, and then I'll choose a flight to test whether or not which forecasts seem to more correctly reflect what was going to happen. And so that's just one of the things you get to play with. I mentioned normalized surface sun. And so in this one, and I've got it really saturated right now. So purple means everything's getting to the ground. If I'm going to scoot the display over a little bit, over here towards the west part of the state, you notice we're getting yellows and greens. So that says that sunlight is not, the model predicts that the sunlight's not going to get to the ground. Well, one of the things I said to look at with that was to go look at where did it say clouds were going to be. And notice that this is cloud base. The greens are in the 13,000 foot range, but notice that we have low clouds in this area, some up, down in the 10,000 foot range. And now let's go back up and look at the solar. And notice that same area was the one that was saying they weren't going to get that much sun on the ground at 2 o'clock this afternoon. So you can use these parameters to cross-check each other, and that improves your confidence when you look at the model output and you say, oh, okay, maybe that's maybe that's the way it's really going to play out. And over on this one, we get the SkySight does not have the equivalent of the solar energy on the ground, but one that you can use is you can use surface temperature, and then in this case we'll jump up here to the cloud cover. So notice that we've got lower surface temperatures in this area. Now that could just be because of the elevation. So, but we'll take a look at the cloud cover. And there's a little cloud cover. So that lower surface temperature is probably because of the higher elevation, not because it's not getting sun on it. SkySight does clouds. Blue are clouds that are generally below 4,000 meters. Green are clouds that are between 4,000 and 8,000 meters. And then the warm clouds are the ones that are greater than 8,000 meters in altitude. So we could go look at cloud bases. Now, notice we were looking earlier at the clouds in this area, and SkySight said, oh, this might not be too bad of a place to go fly. But notice that we've got cloud bases. This is 13, this is 14.5, that's up to 15. But given the height of the terrain back here, in general, nobody wants to be back here and be constrained at 13,000 feet because of the cloud base. You don't want to be back here unless you're up in the 15s and higher. Okay. So this gives you, this is where your local knowledge comes in. Now, one of the things that we looked at winds. So SkySight gives you winds with barbs. So the direction and the velocity. And you can see back here on the higher ridge lines. Down here, you can see that it's crossing the mountain and the Sangre de Cristos, and it's crossing at 20 to 22 knots, that kind of thing. And so the lift that we were seeing with the thermals may have just as well have been convergence, or is possible that it could have been wave, and we'll take a look at that again in a minute. We can look at the overall thermal layer. Okay, that was surface winds. This is the average of the thermal layer from bottom to top. Notice that we've got winds out here on the plains in the 25 to 30 knot range. And back over here in the mountains, it's up over 30 knots. Okay. So probably not a great day. Remember, this whole area was heavily stippled. Let's go back up here and do the, notice that it was heavily stippled with 30 knots average through the boundary layer. You're not going to have thermals penetrating very high at all. So this 6.5 knots to 15,000 feet. Remember, the cloud bases were going to be 13,000 right in here. So all of a sudden, as you start cross-comparing these parameters, you go, no, this ain't going to work. Okay, so like I said, you have to interpret this data. We go back over here on RASP, and RASP does its surface winds at 10 meters. And I'll bring it up just a little bit. And it does flow lines. Okay. And then the colors, the background colors indicate the velocity. So RASP is indicating down here on the Sangre de Cristos in the 36 to 40 knot range. Okay, that's more than what SkySight was saying, but we already know that this is way more. It doesn't matter which one is right. It's either one of them is way more than we'd want to be down here flying it. Okay. And again, that's the surface winds and then the boundary layer. And you can see the 20, the 25 to 30 knot winds out here on the plains. Here's Kelly Air Park, and you can see the velocities over here up into the 30s, going up into 40 knots. Now, one of the things that RASP does very nicely is this boundary layer max up and down, gives you an indication of convergence. Now, the convergence could be orographic lift, an obstruction. So basically what we might call ridge lift. So you can see strong bands right here that are up in the 300 foot per minute range kind of things. Let's go back over to SkySight, and we will go get SkySight's convergence numbers. And notice that SkySight is showing the same basic locations. Let me bounce back and forth. So here's the Sangre de Cristos, and I'll move that down a little bit so maybe it'll overlap a little bit better. Yeah, it did. So here's the Sangre de Cristos. Now, SkySight's saying it's not quite as strong. It's saying 1.5 instead of 3. But again, from a convergence perspective, it's still showing these bands in both models. Okay. One of the things that SkySight can do is it has a wave presentation. So let's start at 13,000 feet. So there's some wave at 13,000 feet down here in the wet valley downwind of the Sangre de Cristos. There's some wave over here downwind of the wet mountains. So that's interesting. That's not bad. Okay. Let's see what in RASP, it does it at millibars. And so millibars, 600 millibars is roughly 14,000 feet. And notice that it's showing wave activity downwind of the Sangre de Cristos, and again, wave activity downwind of the wet mountains. So they are both showing it. There's a difference in the velocities involved, but that's not enough to get worried about. So both of them do a nice job. Now, let's play this game. SkySight has a tool that allows you to look at a cross section, for instance, through a wave system. So from this point over here on the left, across the Sangre de Cristos, into the wet valley, across the wet mountains, and then into the wave that's downwind of the wet mountains. So these are meters over here on the left. So let's pick, oh, let's go in at about 14,000 feet. So right in here, about 4,500. So we can see it's warm. That's good. It's cool, up to 7.5 knots of sync. We get back over here, 2 knots, 5 knots, a little bit higher. It's 6, it's 7. It cools off, but it's only 1 to 2 knots down. Oops, there's 7. And then we get into a range over here where it's nice. Okay. So you can use these tools to give you a feel for what it would be like if you were to try to fly the wave. Now, that was going across the wave system. Let me do it along the wave system. Let's start down here by Silver West and go up here, go north. And so in this case, what this is telling us, here's 13,000 feet is right at the bottom of this. Yeah, okay, here's 14,000 feet. So if we were flying out of Silver West and we got up to 14,000 feet, we could run most of the way up towards Salida and be in wave lift all the way up there. Now, there used to be a wave window over this area, and one of our members took his glider down there, launched, got into the wave system, and set a 100-kilometer speed record, triangle speed record, flying completely in the wave for the entire flight. So this is another way that you can analyze your flight, the potential. Okay, again, we are talking about these are model runs. These are not reality. This is, it might maybe be this way. And unfortunately, we don't get that one with RASP. So RASP does a nice job in helping us do the weather forecast, and that's plenty. It's a wonderful cross-check. And it's also possible, depending on who the person is that's maintaining the forecast for the region, to make these forecasts available to be downloaded. They're fixed images. So for instance, let's say the model runs at 9 o'clock this morning or finishes at 9 o'clock this morning, and you go over to the clubhouse and you stick your USB stick in, download the data file, and these images are timed so that like XC will do RASP. So it will, it's 2 o'clock and then it's 3 o'clock and then it's 4 o'clock. It will put the appropriate image up as the background on your display so you can have these weather images in the cockpit. Again, they are not the current weather. It is the model's prediction, which might be, oh, if I could nestle up close right here, I could have a nice run from down here at Silver West all the way up to Salida and back. It allows you to say, oh, that might be worth trying. Okay. And the same thing is true for SkySight. When I did the cockpit computer talk, I kept saying that the ODN or not just the ODN, but that the new CU Navigator software is missing components that I would like to see it have. The OD2 would download a day's worth of SkySight forecast images and allow you to display them on the OD2. The Navigator software will only download it in flight from the server. It will not allow you to download the full set for the day. So if you run into a place that you no longer have a cell connection, you no longer have your weather data. Okay. So like I say, Navitier still has work to do on the CU Navigator.
Hey,
Now, I
Dave, I
mentioned,
got two questions on this that are
yeah,
relevant. What in SkySight did you select to get the wave along the route with the wave picture on the right side of the screen?
over here, there's on the wave section at the top, it says wave cross section on the top left. and that's what I selected. And then I came out here and clicked once and drew a snap line up through there. And then once I selected the endpoint, that's what put up the wave profile.
Perfect. Second question, because we were on RASP a few minutes ago. Somebody asked, similar to what's at Black Forest Soaring Society, how do we get a RASP, RASP for our local flying club?
Oh. Okay, if you're asking how do you get the forecast, there's a website, and I don't have it handy. There's a website that has a instructions on how to download the model tools, and I think it's got build instructions so that you can build and then define your area and then run the models on your local machine and then make them available to your club. So I would look for RASP. Um, uh, yeah, I would just look for the website or the blog page for RASP, RASP. Maybe go RASP weather forecast.
Thanks, Dave. That's all I got.
Okay. Now coming back over to SkySight. So here was doing the wave was one analysis tool. I'm going all the way back up to the top of the menu on the left side. If you want, and I'm going to zoom in a little bit and so I can click on the Kelly Air Park dot. I told you that there was a point forecast. And so I'm clicking on the Kelly Air Park. The point forecast is more than the skew T. You can get the skew T if you want it, but the point forecast is more than the skew T. In the top portion, here is the clouds. So Friday is over to this line. There's a vertical line, and you can see sunset at 1954 and sunrise for Saturday at 6:07. So there's at least 3 days up here at the top. So today wasn't, it was pretty sunny with some clouds along 4:30, 5:30-ish. The surface heating, it got warm and then dropped off. If there was thermals, the thermal strength starting at about 10:30 was about 2.5 knots. The best it got through the day was about 5.8 around 3:30. The soarable height, remember our airport's at 7,000 feet, so right there it's sitting at 7,000 feet on the ground. And notice that it came up, and so somewhere around 12:30 it got up into the range of a little over 12,000 feet. You could play in that. Your max would have been about 16,000 feet, somewhere around 4:30, and then it dropped off rapidly until about 6:30 at night, and you're back on the ground. Okay, those altitudes I'm reading off of this port in the chart right here, and they line up with the times up here at the top. So we have the soarable height. So here's the numbers. So starting at 10:30, you could have done it at 1,700 AGL all the way up to 9,300 AGL at some point, so up around 16,000 feet. The surface temperature through the day, you can see it steadily increasing, hit a maximum, and it's dropping off. It'll drop off tonight, and tomorrow we'll have nowhere near the amount of heating that today had. The dew point, you know, it was fairly low, so we're fairly dry, and then tomorrow it's going to get drier even still. Down here at the bottom, we have wind. So at some point today, we would have had wind at 23 knots at 170. So that's straight down the runway, but we would have had gusts to 36. So for instance, launching into a 23-knot headwind with 36-knot gust, if I had a rope break at about the time I turned off the runway heading, I could be landing downwind with a 20 to 40-knot tailwind. Might not be a good choice for the day. And then the overall pressure, remember 1013 is standard. This is in hectopascals or millibars. And so 1013 is the standard 2992 equivalent, and notice that we're running fairly low pressure all the way out for the next 3 days. So you can get this kind of information, which is far more than just what a skew-T is. I mean, I can get a skew-T, but, and I'll go back here and get the skew-T, but I get a whole lot more information out of that other chart by saying, give me the point forecast as opposed to just giving me the skew-T. Because now I have to remember what all the lines mean on the skew-T. Doesn't mean it's not useful, but, you know. The other one that it can do is it can give you a route forecast. So I'm going to select Kelly. And you notice that it's creating a bunch of white lines. And what it's doing is it's going out and trying to create, I'm going to zoom out, and you're going to see a bunch of white lines centered on that red dot at Kelly. And what it's doing is it's saying, oh, see the red line going down to the southwest? It's saying you could do a 207 kilometer out and return today. You'd only fly it at 100 knots or 100 kilometers an hour. You might be able to get a 383 up to the northwest. Here's a 182 kilometer triangle. That's at 91 kilometers per hour. If you wanted to try a 600K out and return, it's in pink up here in the top. That means not likely. Yellow means, or green means likely. Yellow means it's a stretch, and red means, yeah, have fun. Okay. The other thing that you can do, though, all right, is you can come in here and you can go, oh, okay, I'm going to fly from Kelly to Dillon Reservoir down to, let's go down to Buena Vista, and I'm going to come back and I'm going to fly the triangle. Okay. So I've got a triangle on there. Notice at the top of the screen, I've got a profile of my flight. The red blobs at the bottom are the terrain. The red line is the soarable height for the flight. So notice that the soarable height is below the terrain in a lot of areas. So we're not going to fly that flight today. Up above it, there's the black line, and that's the thermal tops. And then there's a pink line right here that you can barely see, and that's the top of the condensation level. And then up here, if you're above the condensation level but below the top of the thermals, you can see the gray, and the gray is indicating where the clouds are. So what you can do with this is, I'm going to start over here at 1300, and you can see the airplane's moving, or the glider's moving as I move across, and you can see the change in the background as the weather evolves through the day. And what we were looking at is we were looking at the wave forecast at 13,000 feet. Let's put the thermal on there and run it through the same thing. And notice that it is changing, but not significantly. And, you know, the flight wasn't going to work anyway. The other thing you can do is come over here on the right, and you can select your start time. And so your start time, let's select noon. Notice that it's shifted. And now notice I've got an optimized line. That's these two settings right here. So it's no longer just doing the triangle. It's trying to give me a path that I might be able to fly the flight. Notice now that I've got some real interesting things. There must be an inversion right in this area to see that go backwards. But notice that my soarable height is no longer intersecting the ground in so many places, but also notice I'm no longer flying a straight line between those points. Okay, you can do this, you can use this, and you get a little history of your tasks that you've defined over here on the left side, so you could come back and select it again. And you can put your waypoints in the system. You can get your space definitions. Notice that we've got the Class B airspace and the Class C airspace between Denver and Colorado Springs, respectively. Okay, there is one more capability of SkySight that we need to talk about. And let me clear this. In the upper right-hand corner of SkySight, there is a settings menu. In the settings menu, you set your location. So this one is set for North America, US, Canada, West. There is also a US, Canada, East. Okay, so that's going to set the general area that you're going to fly, you know, that you want your forecast for. And you're going to come down here to account. And in account, you're going to select your type of aircraft. So it's sailplane, paraglider, hang glider, balloon, or plane. And you can set which parameter you want to display when you turn on your system. I have it set for thermal strength with buoyancy shear ratio. I think the default, it comes up on thermal height. And now here's the fun one, this pilot glider factor, and it's set for 100. 100 is the performance of a Ventus 2 with 18-meter span and 45 kilogram per square meter wing loading. If you're flying a 126, those times that we looked at and that flight path that we looked at are not going to be the same. And the way you adjust this is you go to the OLC handicaps and you get a handicap for this Ventus, and then you get a handicap for your 126, and you divide the handicap of your 126 by the handicap of the Ventus, and then you multiply that by 100 and you enter that number here. Okay, and for the 126, that should be about 53. Then what happens, you know, you save this and it goes back and starts over. It resets. And then what will happen is when you put this task up, like I got a short task right there. So you can see what it says that a Ventus 3 should do, an 18-minute Ventus 3. So if it launched at noon, you should be able to do 93 kilometers an hour. You'd be in the air for an hour 58. That's what this table is saying up here in the top right. I'm going to go back up here and I'm going to change this and put in 53. Yeah, it won't go down to 60. Okay. 61 is the number for a 136. So I'm going to put a 136 in, and then we're going to redo this, and I'm going to come back up. And you notice that, I wonder if it stayed. Hang on, let me check something. It didn't stay. What did I do wrong? Oh, let's put 61 in. I hit go back instead of update profile. You have to hit update profile for the new number to take effect. So now let's come back to this little 180 kilometer. So now, if we go back here and launch at noon, we're only going to make 56 kilometers an hour, and we're going to be in the air for 3 hours and 15 minutes. So what this does is SkySight gives you the ability to do what ifs for your specific glider, and you can change those numbers based on your glider. And I have a slide in the package. I'll show it to you later. I have a slide in the package that shows you several different models of gliders with the same kind of information, with that information for them. Okay. Now, you got to put up with my background screen for a minute while I try to undo something I did earlier. Okay. Why are we? Ah, there we go. Yay! I was able to get it back. All right. So we've stepped through RASP and SkySight. The slides, I've got descriptions of the various parameters that we talked about as we were going through those, so you can see those. And you can bounce back and forth between the two models. So some of the things that you end up having to work with. You can download the model data to a cockpit computer. These are static images. They usually replace your terrain background. They're time phased, so the clock in the computer will switch to the next image as the time. But you got to remember, this is still just a prediction from a model run several hours ago. It's handy for maybe over there hints. If you get real-time model updates in the cockpit, if it's a model update, it's still just a prediction. Okay, that's not the reality that you're looking at outside. The other one is that you can pull real-time weather data into the cockpit if you've got a good connection and you've got the software to display the data. The key to remember is the service provided data is always delayed. Figure at least 15 minutes out of date. Even if you're on a direct National Weather Service radar site, for instance, let's say that I went to the radar site at Colorado Air and Spaceport, and I have that site updating. It only updates every 6 minutes, and then that image stays up for 6 minutes. Okay, so and that's if they're on the precipitation update. Okay, the simplified model usage. So this is what I look at when I start on a week. I start on Monday, and I start with what one of our club members calls the picnic forecast. So go pick the TV station that you like their weather forecasting better than the other TV stations for your area, and go look what they say it's going to be next weekend. And I say picnic forecast because it's, you know, are they saying it's going to be rainy, snowy, windy, whatever? Well, maybe that's not a good plan, but it gives you something to start with. Start your RASP or your SkySight, set it for about 1400, and then take a look at lift and height or what's a possible flight. Do the same thing for Wednesday and Thursday, but what you want to look for is you want to look for changes in the weather model and whether or not it would affect the flight, those changes, how they would affect the flight. Now we're getting to Thursday and Friday. Okay. At this point, you should pick a couple of possible flights for the weekend. I try to pick 3. And I'm doing the same thing with the models, but now Saturday's 3 days out on Thursday. So today plus 2 or today plus 3. So Saturday and Sunday might be in there in the mix. So I start looking for the specific flights that I want to fly on your fly days. So assuming, you're working during the week and you got Saturday and Sunday to fly, the RASP model, at least the one for our club, is usually available by 6:30 in the morning. And so, you could get on and review the overall day, like from 11 to 5 p.m. and check out against your likely flights. And then once you're at the airport, again, we get a later model run, and I've got in here that it's usually available by 9:30. I don't remember if it's that early anymore. But what it does then is it allows you to take a look at the updates to the model, sweep it through the soarable part of the day, 9 a.m. to 5 p.m., check against your likely flights, and then download your model data to take to your plane. The key to remember, at least in our area, I've flown some in Virginia, but I haven't really flown a lot there. I've flown some in California, but I haven't flown a lot there. In our little world along the Front Range of the Rockies, it's usually sustainable by about 11:30 in the morning. It may not be cross-country worthy until like between 12:30 and 1 o'clock. Okay. Now you have to remember, this is a simplified view of how I approach coming up to the flying days on the weekend. This isn't a contest. I'm not trying to understand the underlying relationships. I'm just going, am I going to go fly Saturday and Sunday? And if I'm going to go fly, what's a likely flight? I like to always take off with one flight declared. I like to have three flights declared, three flights prepared, so that, if I go east, I go south, or I go west, I've got choices. And again, remember, RASP only goes out about 3 days. SkySight will go out about 6, but remember, anything beyond 3 to 4 days, it gets kind of iffy. I did give you guys the acronyms so that if you're using the models and you run across these, you've got at least the titles. And then the other slide that I promised you was this one. So I went through for the gliders on the left, in the left column in both tables. I went through for those gliders. I got the OLC handicap for the Ventus at 119, and so its pilot glider factor was 100. And then for each of the other aircraft, for instance, I fly a Ventus BT at 15 meters with winglets, and so my handicap is 112, and so I would put in 94 in that entry point under settings, and that should give me those flight parameters, where I could run it and see how long it's going to take, how long I'm going to be in the air, how fast I'm going to fly, stuff like that. It adjusts it somewhat for the type of glider. I also fly an ASH-26E, and its handicap is 118, so it's off by less than 1%. I don't bother changing the number for that. So you can see an LS6, an LS3, JS3s, whether they're the jet or the res, have OLC handicap of 122, so you'd put in 102. 27 ASW-19 is it took over for the Cirrus as the 100 handicap Sacred Cow aircraft. It's got a pilot glider factor of 84. And again, if you're using SkySight to help you plan your flight and to get times on course and possible speeds to fly, you want to use these pilot factors. Okay. Come over to the other column, 24, a DG300, the 126, both of those pilot factors are below the table. The 136 at 64, Pegasus and ASW-20, and then the other one, the Ventus 3, whether it's the FES or whether it's the M, both of those at 18 meter have handicap at 122. So, and there's the formula underneath that to, I didn't hit everybody's glider. So go to the OLC web page and then go to rules. And then in the table of rules, all the way down at the bottom, it's got airplane notes or airplane something. I don't remember the true term, but that's a PDF file with the handicaps listed for all of the aircraft that they have the handicap for in the OLC system. So we're getting to the witching hour. Questions?
Dave, that was awesome. 10 more years, I'm going to get this, I promise. I think we have 2 questions left here. I'm going to go back to the very beginning. We were looking at the GOES satellite. And I'm going to kind of rephrase this question a little bit, but how do you use the GOES satellite images to use that information to calculate your soaring day?
Primarily what I'm looking for Um, the GOES satellite has 16 data channels, and it includes moisture at low, medium, and high altitudes. And their definitions, that's basically from somewhere around 12,000 feet up to about 30,000 feet over that range. So part of it, I look for the moisture plumes from that. I look at the cloud flows. I look at how the winds, you can actually, one of the channels, or maybe it's two channels combined, I don't remember which, you can get you can get winds based on the satellite look. And so basically what I do with those is I either use it to set my expectation for the day, or if the model seems questionable, I go and look at some of the other channels to see if I can get an indication as to, did the model just hiccup, or is it, you know, what else is going on? There might be something else out there that is not apparent from the parameters that the models give you. It only gives you an answer, and it might say, yeah, it's going to be a lousy day. And you go, well, I didn't see anything that said it was going to be lousy. That's when I go look at the satellite imagery.
Perfect. Last question I think we got here is about SkySight, and this was about the OLC competition handicaps. You mentioned using an equation, and I think maybe we got that at the end, but can you clarify SkySight OLC competition handicaps in the equation that you use? That's it right there? Okay,
That's
perfect.
it right there.
Awesome.
So the pilot glide factor, if you take the OLC handicap for your plane, so I'll use my Ventus for an example. So my handicap is 110, 112. I divide that by 119, which is the handicap for the Ventus 2 at 18 meters. And because that's the 100, that's the default setting. And then I multiply that division result by 100, and that gives me 94. And so I would put 94 into that pilot glide factor field, tell it to update my profile, and now the numbers that it gives me should reflect that I'm flying something other than an 18-meter Ventus 2C.
Perfect. Thank you. We do have one last minute question. And again, on SkySight, it doesn't mention units of altitude. Is there a standard of MSL versus AGL?
It depends on the parameters. So for instance, there are parameters in SkySight that specifically say AGL. So for instance, there's a height of the thermal band, and that's AGL. Whereas height of how high the thermals go will be an MSL.
Perfect. Dave, I think we're right on time, maybe 1 minute over. You did a fantastic job. That was amazing. We have no more
Oh,
questions.
one other thing for SkySight, that height of the height of the thermal band, you can use that to get your initial. If you're one of those people that likes to have three height bands and you divide the altitude, into thirds. If you're in the top third, you can run like a scalded cat. If you're in the middle third, you're okay, but you're going to take something. Maybe it's less than what you would have taken if you were in the top band. And then in the bottom third, you're tippy-toeing, hoping not to land out, and you'll take anything. You could take that height of the thermal band, divide it by 3, and convert it over so that you get your initial height bands for the day until you get a feel for how the day develops. So that gives you a nice starting value if you're the type of person that wants to have the 3 bands, and it gives you a little bit of help in your decision making. Now what'll happen is after you've been in the air for a half hour or an hour or two, you will know how the day's developed, and you'll know that maybe the top band is wider than what the arithmetic says it would be, that kind of thing. But it gives you a nice starting place. So that's another thing that the model can help you with.
Thank you, Dave.
All righty. We 2 more sessions. April 19th, we'll be talking about flight tracking. This has been a rapidly evolving over the last 3 years in the United States. This has been, we've gone from just satellite trackers to OGN trackers using our FLARMs and other devices. And so that discussion is going to be rather interesting. I've got an interesting 2 weeks together between now and then to try to put together all the changes over the last 2 years since the last time we presented this. So hope to see everybody 7 o'clock on Friday night on April 19th. Thank you, everyone. Frank, back to you.